Okay, I'm going to work through the Quiz Me buttons on the study plan for Test 2 in hopes this is a good review for you. And you watch this video or do the study plan on your own. Notice it says you earn 2 mastery points out of 12 and you're ready to begin. I prefer not to make a set number of points prerequisite, because then people get jammed up. They're trying to get through the course and take their test, and rather than hold them up with that, I don't make that required, but I do put the study plan in there so that you have questions, you have practice questions, and then the Quiz Me button that will mirror what the test is going to look like. So I'm going to roll through the Quiz Me buttons. They seem to be the ones that take a little bit more time and can slow you down. So, and I might not do all of them like I did on the first test, just to keep it brief, because a lot of times it's repetitive. Again, there's only 25 questions on test 2, and you would go through a lot more practice questions if you did all of these practice buttons in Quiz Me. So let's take a look at the basic probability quiz test that we have in here. This is only one section we have in Chapter 3. So we have a frequency table, and it says use the frequency distribution at the right to find the probability that a voter chosen is in the given age range. And the age range they give us is not between 35 and 44. So the very first thing you're going to do here is add up all of these frequencies. We're going to need that number. So I'm going to do that first and find that total. Okay, so when I add all those up, my total here is 143.9. So there's a couple of ways that we could answer this question. We could add everything except the 23.5, right? And then divide that by 143.9. Or we could take 23.5 divided by 143.9 and subtract that from 1. You can do it either way. So I think it's easier just to take everything but the 23.5, right? We want the probability that somebody's not in that age group. So if I take 143.9 minus 23.5, let's see where that puts us, 120.4, and then I'm going to divide that by 143.9. And that'll give me my probability that somebody is in that age bracket, 0.837. I'm not sure of the decimal places they want here. 3, so that'll work. 0.837. And again, the reason I do the Quiz Me is because it doesn't give you instant feedback. When you right-click here on the practice problems, it'll tell you whether you did it right or not. Okay, so this moves us on to the next one, but it doesn't tell us if we got the previous one correct or not. Okay, so probability experiment consists of rolling a 6-sided die and spinning the spinner shown at the right. Notice the spinner on the right has 4 quadrants to it. The spinner is equally likely to land in each. Use a tree diagram to find the probability of the given event. Then tell whether the event can be considered unusual. Okay, so the event is going to be rolling a number less than 5, okay, and the spinner landing on yellow. So let's think about rolling a number less than 5. What's that? That's a 1, 2, 3, or 4 out of 6. So that's the probability of that event is 4/6. When we see the word end here, that means we're going to multiply. Okay, so rather than drawing out the tree diagram, I think we can just multiply this. The probability that we land on yellow is 1/4. Right? There's 1 out of 4 blocks that are yellow in there. So we're going to take 4/6 or 2/3 and multiply it by 1/4. Right? So I had 4 divided by 6. That's the probability of rolling a number less than 5. And then I want to multiply that by 1 divided by 4. And since multiplication is commutative, that will work. So I get 0.167 if we're still doing 3 decimal places. And this is not unusual because it's not close enough to 0. Generally, we would want something to be less than 0.05 to consider unusual. Okay, so we have another similar frequency table, finding a probability of a range. I think we have a good idea of what that's going to look like. So I just went ahead and submitted the quiz. The rest of the questions are going to be similar to that. It's only 3 of them, just so we can move on to the next section to review. Okay, so we have I want test 2, not test 1. And I'll go to the next Quiz Me. These are our more specific probability distributions. Okay, so here, what is the probability of 4? If this is a legitimate probability distribution, that means I have to subtract the rest of these from 1, and that will be the probability of 4. So I can do this, I'll do it out loud, or you use a calculator, but I would add all 3 of these together and subtract from 1. The 0.23 and the 0.47, I can see that that's going to be 0.7 when I add that together. So plus 11 would be 0.81. So the probability of 4 has to be 1 minus 0.81, which would be 0.19. And we go on to the next question. Okay. So here we want to construct a probability distribution of the numbers that they have in front of us here. So I need to find out what my total is first. So I have to take 7 plus 11 plus 34 plus 52 and so on. I have to add all of those together first. So when I add all those together, I get 194. That's my total. So to get my probability distribution is going to be simple. I'm just going to take each actual frequency, 7, 11, 34, and so on, and divide each one by 194. So 7 divided by 194. 0.036, that goes in my first spot. Then next, what do we have? 11 divided by 194. 0.057. And so on. So I want to find now the graph of the distribution that most closely matches what we see here. It looks like on both ends we start in the tails. This should be our smallest spot, so it definitely can't be A. Now here we have our smallest spot at 0, but we certainly don't have our largest spot at 6, right? Our largest is somewhere in the middle. Okay, so this is 0.036. This one looks like it's way too close to 0.1, right? You see that? To be 0.036. So even without zooming in, I can see this much more looks like in D 0.036 to 0.057 to 0.175. That one really seems to match what's happening with the distribution of numbers. To describe the distribution shape, well, if it looks like this, where we have a long tail to the right, remember that's skewed to the right. If it looks like this, long tail to the left, it's skewed to the left. Both of these two distributions are roughly symmetric. Okay, uniform means they would all be the same, all the bars are the same height. Okay, so we're basically doing the same thing here we did in the last one, so I'll pause there. So just for the sake of saving time, we did not do the third one here, but the first two you can see were completely correct there. So get back to the study plan. Test 2. Let's try another quiz. Find probabilities of a discrete probability distribution. Just one question. Okay, so find the probability distribution number of televisions in a household is given to us, right? So find the probability of randomly selecting a household that has 1 or 2. 1 or 2 would be 0.15 plus 0.26. I think that's 0.41. We just add those two together. Find the probability of randomly selecting a household that has 2 or more. So that would be 0.26 plus 0.58. I think that's 0.84. Just add those two together. Find the probability of randomly selecting a household that has between 1 and 3 televisions inclusive. So that means 1, 2, or 3, and we include the endpoints. So that would be our 0.84 plus 0.15. That's 0.99. And we can see that matches up if we just did 1 minus 0.01. Find the probability of randomly selecting a household that has at most 2 televisions. So it has at most 2. So that's 1 or 2, or 0 or 1 or 2. That would be at most 2. Quickest way I think to get that would just take 0.58 and subtract it from 1, which would be 0.42. Or we could add these two together, right? 0.31 plus 0.02 is 0.42. And we can submit. And correct. Okay. So here we're going to really lean on the calculator for this one. So the first thing I want you to do here is take all of the numbers in the first list, 0 through 7, put them in a list in your calculator. All of the numbers in the second list, put them in a list in your calculator. If you don't remember how to do that, I'll walk you through that now. So if you remember from our very second class, the way to enter data in the calculator is through stat. We hit the stat key and then the edit key. Okay. So if I have lists there, I'm going to clear them. I just go up to the top, so L2 is highlighted and press clear. And now I'll come over, go to the top of L1, so it's highlighted and press clear. And let's just double check. The numbers that were in the first list were just the numbers 0 through 7. So we would enter those. And then right next to those in list 2, we want them next to their partners. So next to 0 would be 0.058, and so on. So it's going to look like that. We have a valid probability distribution. All the probabilities add up to 1. So I'm going to go to Stat, and now we go to Calculate. And what we want is our one variable statistics. Again, don't panic if you don't have the L1 and the L2 set up like that. I'll show you what yours will look like. So if L1 and L2 are not in their spots, you just have one variable stats on your screen. You're going to press second and the number 1 for L1. Second and number 2 for L2, and you'll get the same result. So here's our mean, 3.352. So one decimal place, that was 3.4. The variance, so let's consider that for a second. I'm going to put in standard deviation first. So to one decimal place, my standard deviation is right here. It's 1.8. So that's going to go in first. I feel like that's easier to do. I'll show you why. And now I'll go back to my calculator. Remember, what's the relationship between variance and standard deviation? Variance is just the standard deviation squared. So to one decimal place, they should be okay with that, 3.2. Okay. Interpret the results. The mean is 3.4. So the average student is involved in 3 or 4 activities. The standard deviation is 1.8. So the typical number of students activities deviates from the mean by about 2, we're going to say. And those are our interpretations. Okay, so hopefully we didn't have to take 3.24 and square it. Let me see if that gives us a different answer. Or I'm sorry, what was the standard deviation unrounded? Don't round it. I get 3.36. So hopefully they're okay with us rounding or squaring the rounded version of the standard deviation. And we'll find out. Okay. So same idea here. Just use your one variable stats. Enter that in your calculator, and that should do the trick. So I wanted to check and make sure our rounding was okay, and it certainly was for number 1. So just round everything to one decimal place right from the start. But you're better off getting the standard deviation first, put that in, round it, and then square that to get the variance. The calculator doesn't, you can get the variance off the calculator, but I think it's much easier just to square your standard deviation. There's a lot more steps that you would have to navigate through to find that. Okay, so now we look at a very specific type of discrete random variable distribution. That's the binomial probability, or binomial random variable. So if you remember, the mean is just n times p, 50 times 0.5. So I can do that without my calculator just yet, is 25. The variance is 50 times 0.5 times 0.5. So I think I can do that without my calculator as well. That's 12.5. Okay, I just take 50 times 0.5 times 0.5. And then standard deviation is the square root of the variance. This time we go the opposite direction. We start with the variance, take the square root to get standard deviation. And we see that that's 3.5 to one decimal place. Here's 10th, yep. So I'd like to skip this one. It's really the same thing we were just doing. I want to get to some other types of binomial settings, but we'll go ahead and work through this one. If they're all like this, I'll go to the next one so we can see some calculations. So here's our p-value, 0.37, right? 37% of U.S. voters think that the federal government should get more involved in fighting local crime. You randomly select 6 likely U.S. voters and ask them, so that's your sample size 6, that's your fixed number of observations, and ask them whether they think that the federal government should get more involved. The random variable represents the number, right? So the mean is just going to be n 6 times 0.37. .22. The variance is going to be 6 times 0.37 times 0.63. Where did I get the 0.63 from? 1 minus 0.37. Okay, that's 0.63. That's my variance, 1.4. And to get my standard deviation, I just take the square root of that. And I think we would get the same thing if we took square root of 1.4. I don't think it'll matter. We're going to round to 1 decimal place, right? So let me just double check. So either way, to 1 decimal place, I would get 1.2. Safe there. Okay. In most samples of 6 U.S. voters, the number of voters who think that the federal government should get more involved in local crime would differ from the mean by no more than 1.2. Right. That's what the standard deviation means. That's just interpret the results in terms of. So we take a sample of 6 voters. We might get 3. We might get 4. We might get 5. Okay. On average, we're going to get 2.22. But our number out of that 6 will differ from 2.22 by about 1.2. It's just a definition of standard deviation. So the second part of the binomial random variable setting is where we calculate probabilities either using PDF or CDF. So we want to identify our parameters. P, which in this case would be 0.22. 22% of U.S. adults say they are more likely to purchase during a sales tax holiday. You randomly select 10. So the first one is just a straightaway binomial PDF setting, right? 10 customers, 22%, exactly 2 agree with that. So this is under same place we're in for the normal distribution, second bars, but we have to float around a little bit to find the binomial PDF. And here it is. So our number of trials is 10. The probability of success was 0.22, and we wanted to have exactly 2 successes. So again, if you didn't get the screen like I did, it goes n, comma, p, which is 0.22, comma, 2. And we get 0.298. Nearest thousands. So 0.298, 3 decimal places will do there. Okay. Now, greater than 2. This is going to be a little bit tricky. Okay. The calculator doesn't do greater than 2, but what it would do would be 0, 1, and 2. And then everything else would be greater than 2, right? We want 3 plus 4, probability of 3 plus probability of 4 plus probability of 5, and so on. Calculator doesn't do that. But if we use binomial CDF, and we have to be a little clever about this. We want to add a bunch of probabilities up. There's still 10 trials. The probability of success is still 0.22. But they said greater than 2. So let's have the calculator add up 0 plus 1 plus 2. That's what that's going to do. This always adds up 0 through whatever number I put here. And then I can subtract that value from 1. So I would want 1 minus 0.63. 0.1688. And we'll round that to 3 decimal places, 0.383. And then this one's going to be real tricky. We want all the probabilities 2 through 5, right? 2, 3, 4, and 5. That's 4 of them. So there's a couple ways we could do it. We could do 4 PDFs and add them up. Add up the probability of 2 plus the probability of 3 plus the probability of 5. Just add those together. Or we could do a couple of CDFs and just subtract them. I think that's the better option. Okay. Now, the CDF that we would want to subtract, we would want to take the probability of 0 through 6. So I would do, just try to bear with me. I'm going to add up, 0 through 5. I'm going to go to the top endpoint. 0 through 5, I'm going to add those up with a CDF. But I'm going to have a little bit extra. I'm going to have 0 and 1 included there as well, so I'll subtract those away. So watch what I'm going to do. We're going to take the binomial CDF of everything up to 5. So these parameters are still good. Let's add all the way up to 5. But realize this value is too big, so we are going to subtract from that the CDF up to 1, 0 and 1, because we want 2 through 5, and we want to include 2 and 5. So notice I'm not going to add up to 2 and subtract that away. I would add up to 1 and subtract that away. Okay? And I get 0.671. And that's our binomial PDF and CDF setting. Those will all look pretty similar to one another. Okay, and now we have conceptual questions about the normal distribution, and then also some computative questions about the normal distribution. What is the total area under the normal curve? That's always 1. And, why is it correct to say a normal distribution and the standard normal distribution? So the standard normal distribution is that special norm. They all have the same shape, right? And they all follow the 68, 95, 99.7 rule, but the standard normal distribution is a mean of 0 and a standard. So we can correctly articulate that with choice C. Okay. If a z-score is 0, which of the following must be true? It means that that raw score was equal to the mean, right? Because when we calculate a z-score, we take the raw score minus the mean and we divide by standard deviation. Okay. Draw a normal curve with a mean of 59 and a standard deviation of 12. So B is clearly wrong. So we want to find which one of these seems to follow as close to the 68, 95, 99.7 rule as possible. So of these choices here, the one that looks the best to have 59, if I add 12, and get to 71 and subtract 12 for 40. That looks like about 68%, whereas over here we're at 73. 71 would be closer. It doesn't look like it would encompass enough. So the normal distribution curve is centered at, well, that should be centered at the mean. I suppose that should read standard normal curve, but it's going to be centered at 0 and has 2 inflection points. It starts to bend away there at -1, where we go a standard deviation below the mean, and at +1 above the mean. Okay. What do the inflection points in the normal distribution represent? And so they're the points where the term we would use is concave up or concave down, but it's those inflection points where the bend appears a little different. Okay, so just to double back to this one here, what they wanted was the actual numbers for this normal distribution curve. 59 would live here. That's the mean, not 0. 1 standard deviation below would be 47, and 1 standard deviation above would be 71. Just to clarify on that one, I was a little confused as to what they were looking for there. Okay, the other part of the normal distribution, the fun part, is calculating the areas under the curve, and we use normal CDF for that. So if we wanted the area to the left of 1.43, right? So that's the area below 1.43. I'll give you a picture of that at least one time, if you're not able to picture it. So on the standard normal curve, remember 0 lives in the middle. A z-score of 1.43 would be somewhere a little bit above that, right? So the area to the left of that is this. So if you remember, the way we did that was we would use normal CDF. We pick a really low number like negative 1,000 as our lower limit, 1.43 as our upper, and we have 0 and 1 since it's a standard normal distribution. So if you remember where that is, same place as the binomial PDF and CDF. We have normal CDF. They already have me set at negative infinity. So 1.43, right, is my upper limit. And the mean of 0 and 1 is, mean and standard deviation of 0 and 1 respectively are fine. So I get 0.9236. It's area under the normal curve. So here they make it easy for us. They shade it for us, 1.16. So now 1.16 becomes my lower limit, right? So let me just arrow back over here. Not that far. 1.16 is the lower limit. That's the left endpoint. And then we put an upper endpoint of something really big, like 1,000. And then we still want a mean of 0 and a standard deviation of 1. All of that is still fine. 0.1230. Okay, now we're in between two numbers. It's even easier, negative 1 to 0.9. We don't have to tussle with figuring out what the left endpoint is at negative infinity or upper endpoint. And be careful with this negative sign. Make sure you use this one down here, not the subtraction symbol. So this one went from negative 1 to 0.9, and then I just need the mean and the standard deviation. 0.657. Okay. To the right of negative 2.46. So that means negative 2.46. Oops, don't execute it. That's my lower endpoint, and then my upper endpoint will be something really large. 1,000, 100, million, doesn't matter. .993. And they all look pretty much the same. Negative 2.27 to 0. Still 0 and 1 is our mean and standard deviation. 0.488. Okay, and then the last part of the normal distribution is where we go in the opposite direction with the inverse norm feature. By the way, the last section there, I was rounding to 3 decimal places, and I think it called for 4. So just watch the rounding on those. So we don't lose points on something like that. So here I want the 25th percentile, what z-score would have that. So if you remember, when it says at P25, that's the 25th percentile. We go to second bar still, but we're going to go down to number 3 for inverse norm. So the 25th percentile, that means that it's the z-score on the normal curve that has 25% of the area below it. So if you're thinking right, at 0 here, I'm trying to figure out what this z-score ought to be so that 25% of the observations live below it. So I got a rainbow pen there. It's pretty cool. So that's going to be inverse norm, and the way inverse norm always works is it's area to the left. So it's area left, and then we put in the mean, and then the standard deviation. It will need those two parameters from us. It won't let me write over there. Okay. So for 25th percentile, we just tell the calculator the area to the left is 0.25, mean and standard deviation are 0 and 1 respectively, and that z-score would be negative 0.67. That should make sense to us that it's a negative z-score. Oops, I didn't mean to submit a quiz that quickly. Let's do a couple more of these. Okay. 15th percentile. Same thing. 0.15. Oops. So negative 1.04. Uh, 97th percentile. This should be somewhere up around 2 or 3 standard deviations, right? .88. And we get the idea. And the last part of this normal distribution piece is going to be real applications, right, of inverse norm. So pregnancy length in days for a population can be approximated with normal distribution with a mean of 267 and a standard deviation of 9. So let's think about what we mean by that. On average, the length is 267, but if we go 9 above or below that, that's our 68, 95, 99.7 rule, and so on. So let's think about what they're asking us here. The minimum pregnancy length, what is the minimum pregnancy length that can be in the top 11%? So this number should be bigger than 267. We're looking for a length of a pregnancy that only 11% of pregnancies are going to live above that. So that's inverse norm of 0.89. Where did I get that? It's the white area here. The calculator is always area to the left, so we have to subtract that 11% from 1. So we want, if it's the top 11%, it's the 89th percentile. Inverse norm always uses percentile. The mean is 267, and the standard deviation is 9. So about 278 days, which makes sense when we look at our picture. It's above 2. If you got an answer there that was below 267, you should be able to know that it's too low. What's the maximum that can be in the bottom 7%? So this one's a little bit easier to conceive. No pun intended. So bottom 7%, 0.07, we won't have to do any subtracting from 1. This is how the calculator works. 0.07 is the area to the left. We already have it. So try to have, if you have some pencil paper handy to, sketch that normal curve so you can picture what it looks like, and that'll be about 254. Oh, I'm gonna lose points for these because I didn't round. So the first one to 1 decimal place is 278.0. That's okay. To 1 decimal place here, this would be 253.7. I assume they would just have me round those.